Hi everyone, welcome back to my geometry videos. In this tutorial I want to go over the midline theorem and its application to triangles. So as a quick recap, the sum of the measure of the angles in a triangle is 180 degrees. So we're going to be using this fact a lot. So let's go ahead and start off with this first theorem, the exterior angle equality theorem. So this is not to be confused with the exterior angle inequality theorem, which states that if you have an exterior angle to a triangle, then the measure of that exterior angle is going to be greater than the measure of either of the remote interior angles. So this is not the same thing, this is something different. So we're given that angle ACD is an exterior angle, and we're going to prove that angle ACD is equal to the measure of angle CAB, this angle here, plus the measure of angle ABC, the measure, so these two angles, right? So write down what we know, and then I'm going to apply the fact that the sum of the angle measures of a triangle is 180 degrees to triangle ABC. You get angle CAB here, plus measure of angle ABC plus measure of angle ACB is equal to 180 degrees. If I factor out these first two terms, then we know that the sum of the measures of supplementary angles is going to be 180 degrees. So angle CAB plus angle ABC, this whole thing is going to be supplementary to angle ACB. We also know that angle ACD is supplementary to angle ACB. Why? Because this is a straight line, and if you have to measure these two angles, you get 180 degrees, right? Because a straight line measures 180 degrees. We know that angles that are supplementary to the same angle are congruent. So we know that this thing here and angle ACD are both supplementary to the same angle ACB. So in other words, they're congruent to each other, right? So angle ACD is congruent to angle CAB plus angle ABC. So the measure of angle ACD is equal to the measure of angle CAB plus the measure of angle ABC by the definition of angle congruence. Let's do an example. We're given that ABD is a right angle, this angle here, and we're given that measure of angle ADC is 20 degrees, and we're given that ray AC bisects angle BAD. So we want to find the measure of angle BCA, and we want to find the measure of angle CAD. So we write down what we know. We know that angle ABD is a right angle, so it measures 90 degrees. And we know that the sum of the angle measures in a triangle is 180 degrees. So if we apply this to a triangle ABD, we get measure of angle ABD plus measure of angle BAD plus measure of angle ADB is equal to 180 degrees. Now if I substitute measure of angle ADC is equal to 20 degrees and measure of angle ABD is equal to 90 degrees into this statement here, and simplify it, you get measure of angle BAD is equal to 70 degrees. Now if we look at measure of angle CAD, right, this ray bisects the angle, so the measure of angle CAD is going to be 1/2 times the measure of angle BAD, this larger angle here. So 70 times 1/2 is 35, so measure of angle CAD is 35 degrees. Now measure of angle BCA right here is going to be equal to the measure of angle ADC and the measure of angle CAD, right, by the exterior angle equality theorem. And if I substitute measure of angle ADC is equal to 20 degrees and measure of angle CAD equals 35 degrees into this expression, we get measure of angle BCA is equal to 55 degrees. I'm going to go over the midline theorem. I'm not going to actually go over the proof of it. I think the proof is pretty complicated. But if you'd like, you can kind of pause the video at this point and then kind of look over the proof and work it out. and then just resume at a later time the rest of the video. I'll leave it up to you. I'm just going to state what the theorem actually is. So you have B and C, their midpoints of segment AD and AE respectively. So if you draw this segment BC, it's going to be parallel to segment DE, and the length of segment BC is going to be 1/2 of the length of segment DE. So I'm just going to move on from here. So if you're interested in seeing how it's proved, then feel free to look it over. Let's choose some applications here. We're given that B is the midpoint of segment AD and C is the midpoint of segment AE. We're given that the length of segment DE is equal to 10. What is the length of segment BC? So we write down what we know, and we know by the midline theorem that the length of segment BC is going to be equal to 1/2 times the length of segment DE. So we know the length of segment DE is equal to 10. What's 10 times 1/2? 5. So length of segment BC is equal to 5. Okay, so in this problem, we're given ABC is a right triangle. The measure of angle B is equal to 90 degrees, and we're given that segment AB is congruent to segment BC. We want to prove that measure of angle A is equal to measure of angle C is equal to 45 degrees. So we write down what we know. And we know since segment AB is congruent to segment BC, then in a triangle, if sides are congruent, then the angles opposite those sides are congruent as well. So we know that angle A is congruent to angle C, and therefore the measure of angle A is equal to the measure of angle C by the definition of angle congruence. Now we know the sum of the angle measures of a triangle is 180 degrees. So measure of angle A plus measure of angle B plus measure of angle C is equal to 180 degrees. If we plug in measure of angle B is equal to 90 degrees, and we use, if we set measure of angle C is equal to measure of angle A, then you get 2 times the measure of angle A plus 90 degrees is equal to 180 degrees. You solve the algebra, you get measure of angle A is equal to 45 degrees, and then by substitution into 5, we get measure of angle C is also equal to 45 degrees. Okay, so these last two problems are kind of harder, but they're good problems anyway, so let's go over them. So angle ABC is a right triangle, B is a right angle, M is the midpoint of segment AC, and N is the midpoint of segment AB. And we want to prove that segment MA is congruent to segment MB, which is congruent to segment MC. So we write down what we know, these 4 things. We know a midpoint divides a segment into 2 congruent segments. So in other words, since N is the midpoint of segment AB, we know that segment NA is congruent to segment NB. By the reflexive property congruent, segment MN is congruent to itself. Since we know that N and M are midpoints, we can use the midline theorem, and we know that segment NM is parallel to segment BC. If we take this line AB as a transversal, we know that angle ANM, this angle here, and angle ABC, this angle here, are going to be corresponding angles, right? Because they're both on the same side of the transversal. One angle is in the exterior region and the other angle is in the interior region, bounded by lines NM and BC. So we know since these lines are parallel, if a transversal intersects 2 coplanar parallel lines, corresponding angles are congruent. So angle ANM, this angle is going to be congruent to angle ABC. Okay, so for this one, angle ANM is congruent to angle ANB. Well, this whole line measures 180 degrees, and we know that this angle here is going to measure 90 degrees, right? Because they're corresponding angles. So the measure of this angle is going to be 90 degrees, right? So it's a right angle. So angle ANM is congruent to angle MNB because they're both right angles and all right angles are congruent. We can apply side angle side postulate to statement 6. So this segment MN is congruent to itself, and then this angle relation, and then 5, which is segment NA, is congruent to segment NB. We get that triangle MNA is congruent to triangle MNB. And then we know that corresponding parts of congruent triangles are congruent, so segment MA is congruent to segment MB, right? And we already know that M is the midpoint of segment AC, so segment MA is congruent to segment MC. So we get this relation using 11 and 12. Segment MA is congruent to segment MB and is congruent to segment MC. So if you remember what a radius is, remember a radius of a circle is the set of all points that are equidistant from the center of the circle. So what's interesting about this problem is we're given that this point M here is like a center of a circle that passes through points A, B, and C. So you'll have a circle that goes through these 3 points of the triangle. Why? Because if you would have the radius, right, this radius MA is going to be congruent to this radius MB and congruent to this radius MC. So that's not required by the problem, but it's an interesting property anyway to go over. So okay, this is going to be the last problem. This is also a harder problem, but it's a good problem. So let's look at it. Let's not be intimidated by it and go through it step by step. So we're given that ABCD is a quadrilateral and that M, N, O, P are midpoints of these respective segments, right? And we're going to prove that M, N, O, P is a parallelogram. So we write down what we know. And we know we can draw a segment through 2 points, right, lying in the same plane. So I'll just do that for each of these. So you get segment MN, MO, OP, and MP. And then I'm also going to draw segment BC, right? Okay, so if we look at this triangle ABC, right, M and N are midpoints, right? M is the midpoint of segment AB, and N is the midpoint of segment AC. So by the midline theorem, we're going to get segment MN is parallel to segment BC. If we look at triangle DBC, we know that O and P are midpoints of these segments, right? So we can apply the midline theorem again to get segment OP is parallel to segment BC. We know if 2 segments are parallel to the same segment, they're going to be parallel to each other. So since we know that segment MN and segment OP are both parallel to segment BC, they're going to be parallel to each other. So segment MN is parallel to segment OP. And we know, again, by the midline theorem applied to triangle ABC, that length of segment MN is going to be 1/2 times the length of segment BC. And if we apply the midline theorem to triangle DBC, we get the length of segment OP is equal to the length, 1/2 the length of segment BC. So we know that length of MN is equal to length of OP by the property of equalities, right? Because they're both equal to 1/2 the length of segment BC. So using segment congruence, we know that segment MN is congruent to segment OP. So we know that segment MN and OP are congruent, and we also know that they're parallel. So in other words, MNOP is a parallelogram, right? Because if we know a pair of sides are both congruent and parallel, then the quadrilateral is a parallelogram. So that finishes up my video today. I hope you enjoyed it. I look forward to seeing you during my next videos, and I want to wish all my viewers a good night. All right, take care. Bye.